Today, we are going to get into the core of this storage. First of all, when we talk about storage for databases, when we talk about databases storage, we are talking about disk-oriented logical disk storage. Because as we all know, that the memory is a volatile system. So the data in memory, if the computer is powered down, the data will not be retained. So in order to prevent the data from being lost after a power failure, we assume that all of the databases that are stored are in locations that are non-volatile. And then we are going to build this on the disk database accordingly. Most of the databases that we talk about are geared towards storage logical, that's disk-based storage logic. And the DBMS, what we call the database management system, and its component management, is actually dealing with the non-volatile data and exchanges between volatile storage. And that's mainly from the hard disk to the memory, and then from memory to a part of CPU, for example. And then it goes from storage to computation. So these components are mainly managing my data. How it's organized on the hard drive, how it's organized on the hard drive, or how it's scheduled into memory. The how is organized in memory and then feeding into CPU or some other kind of computing unit or GPU or something like that. So first of all, let's be clear about one thing. If a database is very fast, it may have a lot of limitations, which are at the memory level and not at the hard disk level. Because as you know, from the memory to the hard disk, the I/O is a huge bottleneck. And so our management is also geared towards the logical management of the disk. How to fully utilize the memory, including taking full advantage of these scheduling features and caching mechanisms to accelerate the process and make that database more robust, such as failure tolerance, fault tolerance, and concurrency control. These are the problems faced by databases. The problems with storage and need to solve them. Let's look at the main storage hierarchies. Now, the common storage hierarchies that are used, we basically put it through 7 levels. That is, at the top of the hierarchy, the CPU registries, and the CPU cache, and DRAM memory. They are all actually volatile memory, which means that if you cut the power supply, the data is lost. And this volatile storage, which supports, for example, bytes and fast random access, that means that the program can jump to any byte address to process data there. So it's going to access it faster. It's called memory. And the next level is hard disk, like SSD, HDD, and network storage. They are slow. The smaller I/O throughput means that they are slower to read, but it's bigger in size and cheaper. So the closer you get to the CPU and the memory, it's actually faster and smaller, but it's more expensive. However, this non-volatile storage device, as I said earlier, that I don't need to provide persistent power to keep the data stored. Like my computer, I have on my hard disk. This file is saved at less power. I shut down my computer, and when I turn it back on the next day, when the system rebooted, the file was still there. We wouldn't say because I lost power that all the files were gone. It's usually in blocks or pages, and then it goes to this corresponding storage. In the case of non-volatile storage, in terms of the design of the non-volatile storage, the sequential access is very fast. So we have very fast sequential access, and I'm going to talk about why sequential access is very fast. And then we call it a hard disk. But actually, in this storage, we don't make a distinction between a solid-state drive and a mechanical drive. How do we do that? So we may think of it as a disk or a hard drive. So when they are comparing the 6 different levels, and then we compare them in terms of access speed. And what kind of differentiation is that? Here is a comparison. That is, if you open the cache in level 1 and level 2, it's about 0.5 nanoseconds and 7 nanoseconds. In DRAM, in memory, it's about 100 nanoseconds of access time. In SSD, it's about 150,000 nanoseconds, and then HDD, the network storage, and then the last disk after that. This nanosecond concept, you might have some doubts on that. Let's discuss it in another way. If level 1 cache as 1 second, then the level 2 level of the cache is about 14 times of that. So it's 14 seconds. And the memory part is about 200 seconds. The SSD is about 3.4 days. And then the HDD, so the mechanical hard disk is about 33 weeks. That's about 2/3 of a year. If you are talking about network storage, that's about 22.8 months. That's close to 2 years. And then if it's one of these old tapes or this tape-based storage, that's about 67 years. And you can visualize it like this. 1 second from this, and then 67 years, that's the situation. The case is that it's going to be bigger and slower, but cheaper. From this volatile storage to this non-volatile storage. The top one is this volatile one, and the bottom one is non-volatile one. So there is also some fun fact. In the United States in 2018, a US manufacturer of storage, they actually invented a product called NVDIMM, which is a non-volatile memory. This non-volatile memory is something like this, and there is Micron Logan. It's actually a very common one, a very common design for volatile memory. But it got non-volatile particles integrated into memory. And that's what it's trying to do at the memory level. It guarantees both the access speed of the memory and it's addressed in bytes, but also have non-volatile particles, which is to make sure that when there's a power cut, the data is retained. So it's a blend of volatile and non-volatile. But we're not going to get into the details today. Let's just say, in the spirit of memory, it's the volatile storage, and then disk is non-volatile storage. And then the main conflict we are dealing with is volatile storage. The speed of non-volatile storage and the balance between capacity and cost. In this particular case, using volatile memory could be costly. In fact, even now, 3 years later, this product hasn't become the mainstream yet in the industry. Anyway, thank you. That'll be it for today's section. And our CnosDB is alive now, and you can join our Discord channel on the internet, and you can join our CnosDB Cloud as well. This brings us back to the earlier question. What I was just saying was why sequential read and write is faster than random read and write on disk. This is also something we need to consider when designing a database. We should try to make the database perform sequential write as much as possible, instead of random reads and writes, because if I write data from memory to disk, it actually involves 3 main operations. The first operation is seek_tar. I have a disk, for example, the head needs to locate the track to write the data. So first, I have a seek_tar. This is to read the contents of the target sector. Drive B will move the disk head to the drive wall. Position the head on this track. The time it takes for this process is called seek_tar. Let's say the average time is T1, for example. It's about 3 to 9 milliseconds. The slowest time could be about 20 milliseconds. The second time is the second rotational latency. What is the rotational latency? That is, after I position the head to the target track, then the drive waits for the target sector. The first bit of the magnetic axis is rotated under the head. If it is 5,400 RPM disk, the rotational latency would be about 5 milliseconds. The third is that when I read and write to the disk, there is also a transfer time. So the transfer time, that is, when the target sector is positioned under the first head and then access all data. This positioning to the head and then access all data. Then that's the transfer time. If the data volume is a sector traffic, this time depends on the rotational speed and the number of the sectors per track. You can understand this as density. That is, its data density is fine. The average number of sectors per track on this track is about 400. So actually this time about 0.03 millisecond. If the average delay time for reading a sector is about 9 plus 5 plus 0.03. So a total of 14.03 milliseconds. So you can see the main time, in fact, it is seek_time and rotational latency. So when we read sequentially, in fact, after I seek and then rotate latency, I can just go to this order. I can just read the data directly. If I do it randomly, I need to seek, read, and write. Seek again, rotational latency, read and write again. Seek again, rotational latency, and read and write again. So it will be very slow. This is also why, in the end, we can judge that sequential reading is very fast. And if there is only this transfer time, it is very fast to read 400 sectors. But if I go back and forth to find and this rotational latency, and then its random read and write will be very slow. This is also why when we should design the database disk like this to support sequential read and write accordingly. We know why sequential read and write is faster than random read and write now. Someone in our community asked, in our time series database, CnosDB, most of them are sequential read and write. Is that right? The answer is yes. Most databases are sequential read and write. And our sequential read and write will be heavier. That is, I'll explain that later. For example, we use log structure to store logs, and the storage method is LSM column storage. It is actually convenient for this kind of sequential read and write. Few databases use random read and write. Random read and write is access efficiency and speed. It is really unbearable. So now that we know that sequential read and write is faster than random read and write on disk, we also say that we have our own sequential goals. That is to say, our allowable system design goal is to allow the DBMS to manage a database that exceeds the memory size. If all of our databases is actually operated in memory, then our buffer pool in memory can completely say that the data is buffered. Then there is actually no need, or I say in certain time, that is, except for shutting down or power off, I can flash it to disk once. There is actually no need to handle this disk, corresponding I/O. The second is that my read and write overhead to the disk is very high. That is to say, my disk itself, its I/O overhead is very high. Its access time relative to memory, relative to level 1, level 2 cache, this hard disk is a sharp increase, so we must use some related component or features to carefully manage to avoid this large pause and the associated performance degradation. This is also a corresponding consideration of system design. This is a disk-oriented database management system. We can see that it is actually divided into 2 layers. 2 parts, the memory, in fact, he said that there is a buffer tool related. We mean, first, the configuration, in fact, it is from the hard disk. Then from this hard disk configuration, then flash it to memory. Then the buffer pool in memory, then go to build the execution engine to control it from the hard disk. Then to the memory process, the data of the database actually exists. The data on the hard disk is organized into pages. So its first page is generally a directory page. That is, directory such as a directory page. To operate the data, it actually retrieves data from memory, moves through the buffer pool. Then there is an execution engine. At this time, its execution engine will be like a buffer pool. For example, I get a specific business. Then the buffer pool will also manage the corresponding page in memory. Then return a pointer to a specific page to the execution engine. At the same time, the manager of buffer pool will ensure when the execution engine accesses the page will not be swapped out such as a corresponding operation. So this is also a corresponding process. But some of you might say, this DBMS database management system, related operations, in fact, the operating system also had these functions. For example, I use the management of a virtual memory, or this kind of mmap mapping method. I map a text file content to this address space. Then the operational system is responsible for this hard disk. When the conversion between memory corresponding move, in fact, the operating system can do this very well, or it can do it too. Why do I still need a database management system to do it? In fact, the database management system just talk about high level. This design goal, that is, to support the data size stored by the database, access the available memory size, then read and write hard disk data to the hard disk is very inefficient operation. So we manage these operations well. We don't want to say when the hard disk read the data, there's a large gap. Just that its overhead is very large, a large gap appears. Slow down the speed of other operations. We also hope that the database is waiting for data to be read. For example, when I wait for data processing, in fact, other directions, queries can also run parallel. This high-level design goal, for example, this virtual memory method, it can also be done. For example, I go from physical memory to virtual memory, read a page 1, read page 3, but when I read page 2, in fact, there is this possibility stop this related suspension operation. So if I mmap when an error related to this page occurs, in fact, this process is blocked. So if I want us to include this, everyone in this class and DB class, everyone will say, the database, in fact, I still hope to be self-sufficient, be your own master. That is, I hope I can control the operation. It can also be done better because I know which data will be accessed. Then which queries to run, I have a plan and execution. Related operations. But the operating system actually does not have such functions, or it doesn't provide these operations very well. So operating system, OS, is not your friend. What I was just talking about is what the operating system can do. For example, like MAD-wise, I can tell the OS when you plan to read specific pages. For instance, with mlock, I can tell the operating system not to swap memory to the hard disk. This includes using msync to tell the operating system to sync the hard data of memory to the hard disk. In reality, this is similar to some operations in databases. It's a kind of mmap that can do to some extent replace or have similar functionality. However, it doesn't have a better optimized way from the core perspective. This includes optimization for specific pages, buffers, queries, and other related optimizations. So we hope to put these operations on the database and let the DBMS be better at it. For example, OS is good at correctly ordering these pages or flashing 30 pages to the hard disk. OS can do some specialized prefetching, and replacement strategies in this buffer area. For example, what everyone call LRU, list recently used related strategies, are very good at what they do. However, databases are actually better at it. They are better at things like flushing 30 pages to the hard disk in the correct order, or doing some specialized prefetching. Their buffer replacement strategies, like the one mentioned for LRU, are very good at what they do. When it comes to file storage, at the most basic level, databases actually store data as files. In this sense, operating systems are like databases. They don't need to understand what these files are for, whether they store configurations, metadata, indexes, table structures, or anything else. Only the database management system knows. For example, some databases might use a multi-file hierarchical structure. Like large commercial databases such as Oracle DB or DB2, others might use a single file structure, which is simpler and used by smaller databases. However, the operating system doesn't know the meaning of these files because they are encoded in a specific way by the database. So in terms of database management, the operating system is not our friend. Only the DBMS knows, as the files are encoded in a specific way for a database to understand. This is a database storage manager, a component responsible for managing the database data files. It represents files as a collection of pages and tracks which data is read or written to these pages, as well as how much free space is available in them. Its main purpose is to improve the locality of pages in terms of space and time. It also tracks the configuration of written data and available space. In essence, it's a central, pivotal component of a database. We can also see that a page is actually a fixed-size data block in the configuration. The database organizes data into one or more files, which are stored in pages. These pages consist of fixed-size blocks, and a configuration can include different types of data, such as tuples and indices. However, most commercial database systems do not mix these data types within a single page or configuration. Generally, indices are stored separately from tuples. For example, indices and tuples are not usually stored together in a complete collection, including raw data, metadata, logs, records, and so on. Each configuration has a unique identifier, and the DBMS uses an intermediate layer for scheduling, which can map the configuration ID to the actual physical location on the disk. If the data is in a single file, the page ID can be represented simply by the offset. However, most database systems have an intermediate layer, such as hashing indices or B-trees, to map the ID to the file's offset path in a specific relationship. So the storage manager we discussed earlier performs a related conversion, converting these page IDs to file paths and offset, and then mapping them to the actual physical addresses on the disk. Alright, let's talk about database pages. Most databases use fixed length pages instead of variable length pages. Why? It's mainly to avoid the engineering overhead required to support variable length pages. When a page's length is variable, the system needs to support varying lengths, which can be complex and costly in terms of storage management. For example, if a page is variable in length, the system must track and support different lengths, such as 4 KB, 8 KB, or 32 KB, which adds to the engineering overhead. This information, including the actual length of each page, would need to be stored, which increases complexity and management efforts. Using variable length pages can also lead to fragmentation issues. For instance, when a variable length page is deleted, it can leave behind fragments of different sizes, 4 KB, 8 KB, 16 KB, making it challenging for the database to efficiently fill these fragments. This process would require additional overhead for addressing and flushing the pages to the disk. In contrast, using fixed-length pages avoids this complexity and ensures that each page is a consistent size, making it easier to manage and reducing the likelihood of fragmentation. In most databases, page sizes typically range from 1 KB to 16 KB, with 4 KB being a common and practical choice. Let's also discuss the fault-tolerant write levels, which refers to ensuring data consistency in the event of failure during write operations. When we talk about fault-tolerant write, we are referring to the autonomy of writing operations to storage devices, such as hard drives. For example, if the hard drive's page size is 4 KB, the operating system will attempt to write 4 KB to the hard disk. If this 4 KB write operation is not entirely successful, perhaps due to power failure or other fault, the operation will either completely fail or succeed. there's no partial success in writing. Now, when designing your system, this has implications. If the database page size is larger than hardware's page size, such as an 8 KB database page and 4 KB hardware page, additional operations are needed to ensure the safety of writing data. In this scenario, there is the risk of partial writes. For example, if 4 KB is successfully written, but the remaining 4 KB is not, the system could end up with partially written data, which can lead to data inconsistency. To address this, additional mechanisms for fault-tolerant writes are required. This is why fault-tolerant write levels are defined in databases to handle situations where database page sizes exceed those of the hard drive and operating system. When designing a database, it's crucial to consider these factors. Once we surpass these limitations, we need additional safeguards to ensure the data safety, atomicity, and consistency. Well, this concludes our section for our database system nodes sections. Welcome to our CnosDB community. Our CnosDB Cloud is alive now. You can join our CnosDB Discord in our channel. We will see you next time. Bye-bye.